はい、お待たせいたしました。それでは次のセッションを始めさせていただきます。次の講演は、オレンジツァイさんによるリモート講演、プロキシーログオンは氷山の一角、マイクロソフトエクスチェンジサーバーの新たなアタックサーフェスです。それではオレンジツァイさん、よろしくお願いいたします。
Oh, hi. Hi. It's great to be back to the stage of Kerberos. Thank you all for being here. Yeah, and this January we report a series of vulnerabilities on Exchange server to Microsoft, and named it as ProxyLogon. If you are paying attention to the industry news, you must have heard this name. ProxyLogon may be the most severe vulnerability in the Exchange history ever. However, as we went into deep dive on ProxyLogon, it came to us that it is not just a single bug, but a whole new attack service to help researchers to uncover more vulnerabilities. So to unveil the beauty of this attack service, we will start from explaining the architecture, analyzing the root cause, and ending up with 9 vulnerabilities we find. By understanding the basics of this new attack service, you won't be surprised why we can pop out 0 days easily. Okay, so let me introduce myself first. I'm Orange, and now the principal security researcher at DevCore. I'm a zero-day researcher and focusing on web and application security. My job is to find out the most severe vulnerabilities that can impact the world ahead of the big guys and report them to the vendors directly. Apart from that, I'm also a speaker, CTF player, and bug bounty hunter. I got several awards from my researchers, such as the Pony Awards and the Champion of Pwn2Own. If you are interested, welcome to follow my Twitter and blog. So why were we targeting Exchange server? In terms of enterprise security, mail servers are high-value assets since they are the place to keep corporate confidentials. Exchange server is the most well-known and important mail solution in the world. With this in mind, Exchange has also been the top target for nation-state hackers for a long time. So based on our research, there are more than 400,000 Exchange servers exposed on the internet. Every server represents a company. So you can imagine how severe it could be when there is a critical vulnerabilities on Exchange server. So what have we done? We have reviewed the Exchange security from the architectural levels and find a new attack surface. Through this new attack surface, we uncover 9 vulnerabilities and chat these bugs into 4 attacking exploits. The first and the most famous one is ProxyLogon. It's a pre-auth RCE. And the second one is Proxy Oracle. It's an exploit that can recover any user's password in plain text format. The last one is Proxy Shell. It's the exploit we demonstrated at Pwn2Own 2021. It's also a pre-auth RCE. I would like to highlight that all vulnerabilities we uncovered here are logic bugs, which means they could be reproduced and exploited easily than any memory corruption bugs. The new attack service I proposed also launched a new edge for hackers to research Exchange server. There are lots of vulnerabilities related to my research, such as the proxy not find report by NSA and the proxy token by VNPTISC team. It should be noted that there will be one more attack from me in the near future. However, it's still under the patent process, and we are not able to disclose today. As you can see, all of their names have the proxy prefix. That's also because of my new attack service, and we will explain that later. Exchange is a very sophisticated application. Before we cut to the chess, let me introduce the architecture first. Since 2000, Exchange has released a new version every 3 years. Whenever Exchange releases a new version, the architecture changes a lot and becomes different. The changes of architecture and iterations make it difficult to upgrade an Exchange server. In order to ensure the compatibility between the new architecture and old ones, several design depths were incurred and led to the new attack service we find. So where did we focus? We focused on the Client Access Service, CAS. CAS is a fundamental component in Exchange. The official document indicates CAS is a front end that accepts client connections for all protocols and responsible for routing and proxying connections. CAS was where we paid attention to and where the attack service existed. Because the CAS is located at a very early stage of Exchange request processing, all bugs here are authentication free. So you can imagine how dangerous it is when this fundamental service is vulnerable. So here is the CAS architecture copied from the document. As you can see, the left side is the clients, no matter where the connections come from, either HTTP, POP3, IMAP, or SMTP. CAS in the middle part processes all connections and proxies to the backend service on the right side. The backend service will continue to handle further business logics. And because I'm specialized in web security, so we focus on the web. The CAS web is built on Microsoft IIS. As you can see, there are 2 websites inside the IIS. The default website is the front end we mentioned before. And the Exchange backend is where the business logic is. If you look at the configuration carefully, you will notice the front end is listening on post 80 and 443. And the backend is listening on the port 81 and port 44. It should be noted that the ports are exposed on all interfaces. So you may sense something wrong here. All the ports are open to all interfaces, which means you can access the backend directly. Wouldn't it be dangerous? Yes, please keep this question in mind, and we will answer that later. The CAS is composed of several IIS modules. Applications in front end include the proxy module, which is responsible for parsing all incoming requests, applying protocol-specific settings, and forwarding them to the backend. As for the backend, applications include the Rehydration module, which is taking charge of passing front-end requests, populating the client information back, and continuing the business logic. So here is a question for you. How did the front-end and back-end exchange the information? They synchronize the information and internal status by HTTP headers. For a client request, it will first be handled by the front end, and the request will be passed through several IIS modules, such as the filter, validation, logging, and the last proxy module. The proxy module then picks up a handler based on the current application path, such as the /OWA or /ECP. The handler will do the proxy work and forward the request to the backend. When the backend receives the request, it passes the request to the Rehydration module to restore the original client state and continue the business logics. So our idea is simple. Could we access the backend intentionally? Since the exchange synchronized the information by HTTP headers, it seems like most of the access control is done by the front end. If we can access to the backend without restrictions, maybe there are several internal APIs we can abuse. We all know implementing a proxy is hard, and the front end seems like a well-implemented HTTP client. So if there are some magic tricks to manipulate the context between the front end and back end, it must be fine. So in order to abuse the context, we have to know how the proxy module works first. The proxy request handler is the most important part of the front end. All handlers should inherit this class to implement their methods, such as how to handle the client cookies or headers, and how to proxy the client request to the backend. We separate the methods into 3 sections. The first is request, which will pass and modify the client request. And next is proxy section, which will proxy and send the HTTP request to the backend. And the last section is response. This section will receive the response from the backend and decide which header or cookies should be sent back to the client. Because this handler is important, we will explain the methods one by one. The first method of request section is copy headers to server request. It will decide which HTTP headers from the client can be sent to the backend. As we said, the front end and backend synchronize information and internal status by HTTP headers. So maybe you are thinking, I could forge the headers to confuse something. This is a nice try. But unfortunately, you can see here is a blacklist in the method. The front end blocks several HTTP headers which are used internally. Please keep in mind that the header X common access token is an important one. You will learn this later. The second is copy cookies to server request. The functionality is the same as previous one, but it copies cookies instead. The last method of request section is add protocol-specific headers to server request. This method allows a handler to apply customized protocol settings. For example, if the front-end OWA would like to pass information to the backend, here is the place it can insert information to headers. Besides the customized protocol settings, this method also clones the user identity to a new HTTP header. The identity is the client authentication result in IIS, also consisting of your security identifier. The method serializes it to a string and puts it into the headers, which will be forwarded to the backend later. So as of now, you know how the front end and backend synchronize your identity. They do it by the header as common access token. Once the request passing is done, it will lead to the proxy section. The proxy first uses the get target backend server URL to calculate the URL where the front end should send to. This method is also a buggy place and full of vulnerabilities. We will discuss this later. The second step of proxy is create server request, which first initialize an HTTP client, sets up the HTTP method and headers, and forwards it to the backend. We mentioned that posts in IIS are open to anyone, and this is dangerous. That's why Exchange has a mechanism to avoid the situation. While the front end is creating a request, it will generate a Kerberos ticket and put it in the authorization header. This header will be sent to the backend along with the request. So how does backend know which connection is from a valid front end? By verifying this Kerberos ticket. We look into the generate Kerberos auth header and know that the header is generated with the HTTP SPN of the Exchange machine account. If you observe the traffic between the front end and backend, you will see two headers shown in the request. One is the authorization header, which is the Kerberos ticket used to indicate you are a valid front end. The other is the header X common access token. It's a serialized token, indicates your identity. For example, if you log in with the name orange, the header is the serialized result of your security identifier. After sending the request to the backend, the front end receives the response and enters the last section. The response section is similar to request. It checks the response from the backend and decides which headers or cookies are allowed to be sent back to the client. So now you understand how the front end works. Let's move on to see how the backend processes and populates the request from front end. The backend Rehydration module first uses the method to check whether the incoming request is authenticated or not. It is the time to leverage the Kerberos ticket the front end generates. By handing over the ticket, the backend knows you are a valid front-end now. The backend then call the method try get common access token to restore the user's identity from front-end. The method retrieves the header, deserializes it back to the original access token, and put it in the HTTP context object for later use. So far, you learned how the front-end and back-end synchronize the user's identity, and how the header X common access token plays an important role in the CIS architecture. Since the method just checks if the user are logged in or not, it doesn't check the identity. Here comes a question. Could we authenticate as a normal user in the backend? If we access the backend directly and authenticate with a normal user, we can specify whatever values in the header X common access token and impersonate as any users. The idea is good, and actually, you can pass the IIS authentication of the backend. But there's one more checkpoint. The method is token serialization allows verifies the current logged user, and there's a rehydration exception if the checkpoint is failed. It checks if you have a token serialization right. By default, only the Exchange machine account has this right. So that's why the Kerberos ticket generated by front-end can pass this checkpoint, but you will fail even you are using the correct credential. So here is a quick summary. When there's a client request, the front-end IIS first tries to authenticate the request. If succeed, the front-end serializes the user identity and adds it into the header as X common access token. The front-end then generates a Kerberos ticket by HTTP SPN and puts it into the authorization header. It will forward these headers along with the client request to the backend. The backend also tries to authenticate the request at the beginning. The Rehydration module will verify whether the user have the right of token serialization or not. Since we are using a Kerberos ticket generated by the front end, we passed. Lastly, the Rehydration restores the user identity from the header X common access token and continue the backend business logic. So far, we briefly explained the communication between the front end and backend. Let's start a hack. Okay, the first exploit is ProxyLogon. As introduced before, this may be the most severe vulnerability in the Exchange history. ProxyLogon is checked with two bugs to get the RCE. One is an SSRF on the front end, and the other is an arbitrary file write on the control panel of the backend. Where is ProxyLogon? The bug is mainly located at the proxy section in the front end. We mentioned that the front end handlers calculates the backend URL and forwards the request to that URL. One of the handlers is in charge of processing the static resources. It will assign the backend target from the cookie. So you will figure out how simple this bug is after learning the architecture. The front end treats the user's subscribed cookie as the domain name, and the domain name will be concatenated as the backend URL. We use a bit of parsing tricks to enclose the URL and force the exchange to fetch example.com. The exchange will then return the whole response back to us. So what is the root cause of this arbitrary backend assignment? As we mentioned that the Exchange server changed its architecture while releasing new versions. This cookie is a quick solution for Exchange to map the front end in new architecture to identify where the old backend is. So it looks like a design step to adapt backward compatibility. So with the backend, with this arbitrary backend assignment, we have a super SSRF that can control almost all the requests and get all the responses. And the most impressive is that it will generate a Kerberos ticket for us, which means even when we are taking a protected and domain-joined HTTP service, we can still hack with the authentication of Exchange machine account. So thanks to the super SSRF, we can leverage the internal API /ProxyLogon.ecp to get a validation to access the control panel. The API is also the reason why we called it ProxyLogon. As for the rest of the exploitation, I believe there are already lots of technical analysis out there. We will skip it today for the consideration of time. We will not do the demonstration today, but if you are interested, welcome to check the demo on our website. Next, I will be sharing details about Proxy Oracle. Compared to ProxyLogon, Proxy Oracle is an interesting exploit with a different approach. Proxy Oracle would allow the attacker to recover the victim's plaintext password simply by leading them to a malicious link. We use a cross-site scripting and padding Oracle to complete the exploit. First, we would like to explain how the OWA or ECP authenticate users. If the native IIS authentication is used, an ugly prompt will pop out and asking you to enter the password instead of this fancy interface, which means Exchange is using a certain mechanism to ask you the transformation between credentials and cookies. So let's take a look at how this fancy interface is working with the original architecture. Let's get back to the CIS architecture. All the OWA and ECP login mechanism is done by the phone-based authentication module. The FbaModule is an authentication module prior to the Exchange front end and responsible for converting the username and password into cookies or translating cookies back to the original credential pairs. The implementation stores your username and password in cookies directly. Of course, the cookie is encrypted to avoid bad guys catching your password in plain text on the fly. If you read the login traffic carefully, you will see several cookies which stands for your identity. For the later mail operation, you have to attach cookies to identify who you are. Among all cookies, there are 5 important ones with the prefix CA data. You can see from the screen, the CA data contains your encrypted username and password. Here is the pseudocode for the encryption logic. Exchange generates 2 random strings as the IV and key for every session. The IV and key will be sent and stored on the client side. However, to avoid someone stealing the cookies and decrypting it with the IV and key, Exchange uses RSA to encrypt with its private key again before sending. The Exchange then uses the AES to encrypt your encoded credential with the IV and key and put the result into the cookies. And yes, you can find paying oracle here. Exchange tags the CBC as its paying mode. If you are familiar with cryptography, you must know that CBC is vulnerable to the paying oracle attack. The Exchange implementation catches the paying error exception and returns immediately. When the login process fails, Exchange redirects the HTTP back to the login page with an error code. And due to the return, we have an oracle here. If the encryption fails, the error code is 0, which stands for none. And if we corrupt the cybertext successfully, the Exchange will try to log in with the corrupted credential pair. And at this moment, the result must be a failure and the error code is 2, which stands for the invalid credentials. By differing from the error number, we have an oracle to recover the plain text. So now we know we can decrypt any cookie with the paying oracle. But the problem is how to get the cookie from the victims. In order to get the cookie on clients, we uncover a cross-site scripting to chain together. But it comes up with another problem. In Exchange, all sensitive cookies are protected by HTTP only. So we can't access the cookies by JavaScript. So what can we do? Since we can execute arbitrary JavaScript on the client side, why don't we just insert the SSRF cookie, which is used in ProxyLogon? Once we add a cookie to the browsers, we can sniff and take over all the users' web requests. All we need to do is to sit on our server and wait for the cookie to come back. I will elaborate the process further. We first send a malicious link to the victim. Once the victim triggers our XSS, we insert the SSRF cookie to pretend we are the backend of Exchange. Then the Exchange server becomes a proxy between the victim and us. We will take over all the traffic and bypass the HTTP only to get the encrypted cookies. Okay, the demonstration. Because the time consideration, and I will also skip the demonstration today. If you are interested, you can follow my blog to see the demonstration. Oops. And the last exploit I will share today is ProxyShell. This is the exploit we demonstrated at Pontoon 2021. The result of ProxyShell is the same as ProxyLogon. An authenticated attack can execute arbitrary command on the Exchange server. But the exploit chain is different. ProxyShell is checked with an SCL bypass in the front end, an elevation of privilege in the backend PowerShell, and an arbitrary file write to get the RCE. So here is the ProxyShell. The first pre-auth bug is also located at the backend URL calculation. ProxyShell begins with a path confusion. Exchange has a feature called the explicit logon feature. This feature is used to display another user's mailbox or a calendar in a new browser window. Of course, the displayed mailbox must have to be configured with permission to publish first. In order to open with a single GET request, the URL format must be simple, and the mailbox address must be included in the URL, such as the highlight part in the slide. The Exchange normalizes this spatial URL and reroute it into the existing handler. Of course, the path is not the only way to specify the mailbox address. We find that a special case in the auto-discover handler. Exchange will consider address from the query string if the path ends with /autodiscover.json. After getting the address, the handler tries to normalize the URL. You see that Exchange won't conduct too much checking on the pattern of the removing mailbox address, which led us to use the substring to erase any part of the URL. As you could see from the slide, this is the URL we will be visiting. And this is the mailbox address we use the query string to specify. And here is the part will be removed from the Exchange according to our pattern with the address. This is the actual URL the request will be sent to the backend. As for now, we can access any Exchange backend again. Also, this bug is not as powerful as the SSRF in ProxyLogon. It's sufficient to access arbitrary backends. We try to access the API interface to identify our privilege. From the screenshot, you could see that we did access the backend with the Exchange system privilege again. So here comes the post-exploitation part. The approach of original ProxyLogon fails due to some Exchange in-depth protections. So we have to discover a new approach. Now let's turn the focus to Exchange PowerShell remoting. PowerShell remoting is a feature for Exchange for automations. Through the defined PowerShell commands, users can read mail, send mail, and even configure settings by command lines. The Exchange PowerShell implementation is built upon the PowerShell API. By calling the API, Exchange could realize a PowerShell server and uses the run space to limit and isolate the command execution. All the operations are based on the WinRM protocol. It should be noted that although we can access the PowerShell backend directly, we can't still interact with it because we are the system. We will fail the business logic since there is no mailbox for the system user. We also can't forge our identity by the X-common access token due to the blacklist in the front end. So what should I do? We dive into the PowerShell server implementation and find a piece of code that extracts the access token from the URL. The code is sitting after the IIS backend authentication. And before the Rehydration module, it checks if there is no X-common access token. The code will call out another method to get the access token from URL. The common access token from URL is a short method and retrieves the value of XRPS CAT from query string, and then deserialize it back to the access token. As of now, we have an elevation of privilege because we can access the PowerShell backend and specify the access token directly. The intention of this operation is to be a quick proxy for internal Exchange PowerShell communication. By abusing this feature, we can impress that as any user. But here, we use this EOP to downgrade ourselves from the system user without mailbox to Exchange admin. So I can now ask you the arbitrary PowerShell command as admin. And then the last piece of the puzzle is to find a post-outh RCE to chain everything together. Because we are the admin and there are hundreds of Exchange PowerShell commands out here, it's easy to find a post-outh bug. We abuse the command new mailbox export request to export a user's mailbox into the web root to be our web shell. So let's chain everything together. We first deliver our encoded web shell to the target mailbox. And we then launch a Windows PowerShell client to connect to our proxy server. We use a proxy server because we have to modify the WinRM protocol to rewrite the path led to the vulnerable auto-discover handler, which will eventually trigger the path confusion bug and add the access token to the query string. Once the session has been established, we can ask you the PowerShell command to grant ourselves the mailbox export law and invoke the mailbox exporting. And enjoy the shell. Okay, the demonstration, but I think the time is a little bit strict, so we also skip it today. Okay, let's talk about mitigations. Since it's an architectural problem, it's hard to mitigate the attack service with one single action. All you can do is keep your Exchange server up to date and with the support of the ACL or firewall to not externally facing to the internet. Microsoft has enhanced the CAS architecture in April. The authentication part of this attack surface has been reduced in this patch. So if you are lazy, please update to the April patch at least. And if you are super lazy, maybe you can give a shot at the Office 365. It's kidding, yeah. Okay, this is the end of my presentation. If you have any questions or want to see the demo we skipped today, here's my contact information and blog. You can visit it. Thank you again for being here. Thanks.
はい、オレンジサイさんの講演でした。ありがとうございました。本セッションは質疑応答はございませんので、以上で終了となります。